Okay, very good morning to all of you. Welcome to Frontier Lab monthly webinar. And as you know, we have been conducting this webinar every month with different topics related to pyrolysis GCMS application. In today's webinar, we will be sharing about trace level microplastic analysis, particularly like microgram and nanogram using this pyrolysis GCMS. I'm Dr. Karthikeyan Sadrugunan, Technical Marketing Manager for Frontier Lab, to cover the business in Southeast Asia and India. Yeah, thank you for joining. Also, I'm happy to see Professor Uthani Sensei, who is also our collaborator, and his contribution is substantial to our development on this application. So it's really good to see him joining this webinar. Okay, I hope you all can listen my voice. I'm audible. If not, please put a message on the chat box. So, and similarly, if there are questions during the talk, please post your questions on the chat box. We will address it at the end of the webinar. Just for the benefit of some of the audience who may be joining our webinar first time, I just want to briefly introduce Frontier Lab. Frontier Laboratories is a Japanese organization actually who manufactures this analytical pyrolyzer. And also we have other product called tandem microreactor and microreactor for biomass research applications. And we have a unique ultra alloy metal capillary column. So if you want to know more about Frontier Lab and Frontier Lab portfolio, please visit www.frontier-lab.com. Yeah. Okay, so let's start with a very brief introduction on microplastic. Definitely, this is something that we have been hearing for almost 2 decades, and there were like different directions in the past, but now there are some level of harmonization and also good level of agreement, so that the research is able to advance and address the challenges and issues. So microplastics are like particles, like plastic particles that are the size of like 5 mm and less. So it can be like diameter size, or even for fibers, it can be in terms of the length. Okay, and as you know, the sizes classification that it starts from like microplastic, mesoplastic, microplastic, and even nanoplastics. Yeah, in terms of the toxicity and also the impact on human health, people are even started looking into the nanoplastic, but it's like far ahead for us to really have better understanding on this. Today, at least, we have very good understanding on this microplastic. And within microplastic, okay, there are like 2 classification. So like small microplastics and large microplastics. So 1 mm to 5 mm are classified as large microplastic, which is something is not difficult to analyze, not difficult to separate. So the challenge is on small microplastic, which is 1 mm and below, particularly when it goes to microns level. Okay, so this is where the challenge in terms of sample collection and analysis. Okay, similarly for nanoplastics, the classification or the definition is particles that are 1 micron and less below are classified as nanoplastics. So the impact on marine life by accidental ingestion and health effects by concentration of POPs are the different things that people are speculating, or the hypothesis because of which people are trying to pay attention to this emerging contaminant microplastic. Okay, so let me quickly check the chat box if any comments or anything, so that I can just give me a minute. Okay, I think I have already done that part, so it should be. Okay, sorry about that. Yeah, so thanks for putting that message. Yeah, as I said, people are interested in and small microplastics, which is of 1 millimeter and below. And similarly, there is a considerable interest in nanoplastic as well. And today we will be talking more about microplastics, but in terms of the mass-based analysis, where we will talk about microgram and nanogram. Okay, so that is what you will learn from today's webinar. So where do we find microplastics? Everywhere. So frankly speaking, so even in human and different organs, microplastics are found. In the environment, yes, beach, then waters like seawater, river water, everywhere, so even in biota. So if you really want to look at the distribution or fate in transport, it's not enough to just look at the waters alone or sediment alone. It's important to look at the all environmental compartment. But still, we do not have very good understanding in terms of the data distribution. So in the environment, there are like ample number of reports. Okay, the presence of microplastic in beach and natural like seawater, river water, and sediment also in biota. So this is actually extract from a WHO, okay, so which shows the microplastics are shown to pass the intestines into the blood and potentially into the other organs. That means one can expect the presence of microplastic in different parts of the human body in organs. And there is another study shows the presence of plastic fibers in 87% of human lungs. And there are some researchers in the Europe, Netherlands, who have shown the linkage of cancer diseases with the microplastics of the fibers presence. Okay, so there are considerable evidences on these things, but what is acceptable, what is alarming is something is still not fully understood. And another report from WHO is also like recommending to start monitoring drinking water for microplastics. As you all know, very recently, California state has announced the monitoring of drinking water supply in California for 4 years to look at the baseline data of this microplastics distribution. So one of the reasons why we are concerned about this microplastic, because it may get into our food chain, so finally entering our human body. Because during this food chain cycle, so it can also get enriched. So what you see in the water body or sediment uh, doesn't need to be the actual concentration that comes to our plate. During this process, it get enriched, so you may see a higher concentration in the food products. This is what the hypothesis is, because of which there is a lot of concern to see how we can control and mitigate this microplastic contamination. So this slide shows a few reports, very recent reports. The one on the right side is investigation of microplastics contamination, okay, in blood cockles and green missiles. So the reason why I put this article here, they have reported the microplastics in terms of particles. Okay, like they have put in blood cockles like 11 plus or minus 5 particles, and similarly in another location is like 6. So when we talk about 11 particles, so what is the mass of this 11 particles is what sometimes we are like interested to know to assess its toxicity. So for this reason only, people are looking at mass-based analysis. And particularly when we talk about this kind of very few particles, so they may be already in microgram, sub-microgram, or like nanogram in terms of the mass. So we need to have a technique that can really analyze such low concentration. So this is where we see the potential use of pyrolysis GCMS, which can really do the microgram and nanogram level analysis of these microplastics. Okay, on the right side, you have like two other reports that shows the microplastic in human blood and also another one in sediment. So these two papers, they have used pyrolysis GCMS. So you will see the trend, because slowly it is shifting towards pyrolysis GCMS. And many of these reports, if you read, you will understand, okay, why they are looking at a mass-based analysis than the particle-based. But we do not want to eliminate, okay, the particle-based analysis also. But on long term, for routine monitoring, one can anticipate the mass-based analysis, which can be like fast and also simple for a large-scale monitoring exercise. So international agencies also looking into this and see how they can really guide the community to address this problem. UN government agencies urges the ban of microplastics, okay, in cosmetics and personal care products. Okay, as the reason why they talk about this, number of scientific investigations has increased along with the public interest and pressure, obviously, because people make noise, so they have to address this problem. But still a lot of work need to be done. So that is the reality or fact. European Commission would put forward, okay, in 2022, a legislative proposal to reduce the release of microplastic in the environment, okay, in addition to the microplastics to the products. So when you talk about the microplastic source, there are two possible sources. One is the use of cosmetics where the microbeads are used. So after the use, they are being discharged to the environment. So other one is the secondary microplastics are really produced or generated from the macroplastics due to unintentional disposal in the environment due to weathering. So that also cause this generation of microplastic in the environment. So WHO calls for more research on microplastics. Okay, again, based on their previous research, what they say, the particles above 130 micrometers are not likely to be absorbed by human body. Okay, so that means this is also some guidance. So if really we want to know about the size effect, so people have to look at the particles of 130 microns and below. So this is one kind of guidance from WHO. So as I said, there are a lot of difference in sampling and sample preparation and analysis. So yeah, ASTM also trying to come up with a standard method for sample collection, sample preparation, and sample analysis. But at this moment, they are only in draft stage, so it has to go through multiple stages before the standard method will be available for public use. Okay, so one thing that I want to highlight here, so ASTM method, which is in draft mode, has recommended pyrolysis GCMS also technique for microplastic analysis. So if you really want to put your foot in front, so definitely you should consider looking at this technique for microplastic research. Okay, before going to the analysis part, I just want to briefly share the sample preparation part. Okay, so in environmental samples, there are three kind of matrices where people are looking at the microplastics distribution. Okay, one is the water samples. So this water sample can be drinking water, river water, or sea water. So normally you have to separate the microplastics through a filtration. So this is what recommended. So if you expect very high concentration, then probably small volume filtration may be sufficient, 1 to 2 liters. But some of the natural waters, the concentration may be very low, so you may have to go for large volume filtration. Currently, people are using this nylon mesh, but again, there are some new developments where they can also use some kind of stainless steel mesh to minimize contamination from the sampling equipment as well. So water samples is always you do a simple filtration or a kind of thawing, so in the cruise and all, they use the large volume sample collection for plankton uh, collection. The same plankton net can be used for this microplastic also. So only thing you have to use the smaller size mesh for this. So this is a kind of summary from one of our collaborator in Germany. Okay, so where they have collected seawater from North Sea and on average they are collecting about 200 liters. Okay, so as I said, for seawater analysis you really need to do a large volume sample collection, and this is something you cannot do through a vacuum filtration. So you have to use this plankton collection net or something equivalent. And this after concentrating the microplastic, then you can again collect them on a small filter paper, and this filter paper can be directly analyzed by pyrolysis GCMS. So just to have an idea how the concentration ranges are, because you can see they're all in very low concentration, like less than 10 micrograms. Some they are really like even less than 1 microgram. So the question, are we really able to analyze such low level, is the question that we are trying to address or answer. So this is for sediment sample. Okay, for sediment sample, it's always you have to start with the density preparation, the density separation. Excuse me. So after that, you may have to do a slight like organic treatment just to get rid of the organic matter. Then you filter them through a small size filter. Then this can be analyzed. Okay, so in this case also with 1 kilogram of sample, the concentration what you are seeing are in the order of like 2 to 10 microgram per kilogram. So that means ppb level of concentrations. So third one most commonly analyzed is the biota, okay, like fish or other like green mussels. So this is really organic rich matrix. Okay, so you have to do some kind of like chemical oxidative digestion. Okay, and also the density separation first, followed by the enzymatic chemical oxidation. So where you can use alternate like Fenton's reagent also. There are reports that shows both approaches are working. So we do not really have to say which one is good, but based on the practicability, most of the people are using the Fenton's reagents. Okay. But our collaborator back in Germany, they are using the enzymatic oxidative digestion. So after this multiple step separation, finally, yeah, you are again concentrating and taking them, collecting them on a filter. In this case, you use this anode disc or GF filter of smaller size, like 10 millimeter, so that you can easily analyze this sample directly. Okay, so this is very brief kind of explanation or description how the samples are prepared for microplastic analysis. For water sample, it's a filtration followed by this analysis. For sediment, it's a density separation, some organic treatment, oxidation treatment, then the analysis. For biota, it's actually density separation, oxidation, then the analysis. Okay, now we come to the main part of this webinar, okay, the analysis. How the microplastic analysis are being done in today's world, okay. So definitely spectroscopic techniques are widely used, okay. Starting from optical microscope, then people have moved to FAR, ATR, then Raman, then micro FAR, then micro Raman, okay. And each of these techniques has got its own advantages and a kind of limitation. So this is something we do not want to discuss much. So, and as I said, it is based on your objective. Okay, so if you are really interested to look at the particle size based analysis, and spectroscopic technique is what something you have to consider. But to complete your assessment, you may still have to do the mass-based analysis, because just by looking at the number concentration of particles, you may not be able to complete the assessment. Okay, so this is our feeling. So as we say, we do not want to really say which one is good. At this moment, we can say this is complementary to each other, you know, because we are still trying to improve our understanding on this microplastic impact. On the right side, you can see that micro FTAR, okay, the micro Raman, as you all know, it is non-destructive, but it is widely dependent on the particle, okay, particle size and shape. So sometimes you may have false estimation because of the size, the shape issues. And particularly when you are doing a very small concentration and very small size, you need extensive sample preparation time. Also, the analysis time is longer. But again, so there are some automation has been developed in this technique as well. So definitely one cannot eliminate, because even FTIR, ATR, or the micro FTR can do fast analysis in 1 hour also with some improved software system. Okay. On the other hand, pyrolysis GCMS, okay. So this is independent of shape and size. So definitely this is not a limiting factor. And we don't expect any contamination coming from inorganic, which can be a case in spectroscopy, because some of the pigments may interfere in your spectra. So it may cause some interference. But in pyrolysis GCMS, you don't expect this. And compared to a spectroscopic technique, it requires shorter analysis time. Okay. And software development also make your data analysis very fast and simple. Okay, challenges, yeah, again, is destructive analysis. So one time you use up the sample, then you cannot try anything with the same sample. So you have to go to the field. So you have to be very cautious handling the sample, so that you don't run out of the sample before you really get the data for your sample. So these slides briefly summarize, okay, the analysis of environmental microplastics from FTIR, Raman, or both. Okay, so basically, as I said, all these techniques have been widely used, but here I just want to have a couple of points. Okay, for example, in particle B, okay, the paint particles, okay, along with this TiO2 also identified as microplastic. So this is one thing that you may face when you are using spectroscopy. So some of the interference from the pigment or the inorganic pigments. Similarly, yeah, the particle C is a polyethylene with a blue colored pigment. So one thing is, like, it is well documented, the interference from some of the pigments. So you have to take enough precautions to minimize such interferences. And also it has got its own analytical challenges. So particularly when you talk about ATR, you have to make sure that your space is as smaller as possible. So for micro Raman, yeah, again, when you do the micro Raman, the colored plastics and interference by fluorescence, the additive fluorescence may be a kind of interference that one may face it. So compared to the spectroscopic technique, the pyrolysis GCMS can analyze the whole particle, okay? Whereas the spectroscopic techniques are like generally collecting the information, surface information, but it is not necessarily like true for a microplastic particle, because the particle itself is very small. So hopefully, yeah, it is collecting the entire particle, but generally the spectroscopic technique is only meant for surface analysis. So so there is some advantages with pyrolysis GCMS over spectroscopic technique, but again, as I said, at this moment we have to see both are complementary. So this is another spectroscopic technique where they have put FTIR and Raman together. Okay, so the advantage of this technology, they can go even below 20 microns. Okay, so yeah, now we move on to the pyrolysis GCMS. So the points that I want to highlight on the spectroscopic technique, okay, the spectroscopic technique, IR or even LDIR or the micro FTIR, they're all shown like proven to be working for particle size of 20 microns and above. Okay, but it will have its own challenges for sample preparation, analysis, and data interpretation. Okay, whereas any particles below 20 microns, may be a challenge with spectroscopic technique. And we really don't know whether all particles are like 20 microns and above. So that's why people are looking for alternate approach where it can do the analysis independent of the size and shape. So when it comes to pyrolysis GCMS, yeah, it can do 1 micron, it can do 10 micron, it can do 100 microns, so no limitation. So that way you can minimize or avoid one step of screening, because if you want to do by FTIR, you have to make sure that your particles are of about 20 microns. Whereas with pyrolysis GCMS, as long as you are able to collect your particles, you can do the analysis directly. Okay, so pyrolysis GCMS analytical principle. So basically, pyrolysis is nothing but a thermal analytical technique where you are using high temperature in the absence of oxygen. Okay, so that leads to thermal cracking. So the macromolecule into micromolecules. So these micromolecules can be seen as used as a fingerprint for identification of this macromolecule. Okay, so this is actually most abundant macromolecules or the pyrolysates, so that has high sensitivity and they are chemically most significant, so the identification can be more reliable. The ion chromatograms for selective and sensitive polymer identification, even in complex natural mixes. Yeah. So we can do the full scan mode to assure that we are not missing any information, but we can also use the same data for extracted ion chromatogram to look for specific chemical information. On the right side, we have a simple illustration of this polystyrene. So polystyrene, when you do the pyrolysis, the GCMS, you generally get to see three peaks. Okay, that is a styrene dimer, and styrene trimer, and they all have this mass spectrum with the biomarker ions. So these ions can be used for identification and quantification purpose. So this is what basically the approach in pyrolysis GCMS. So for each polymer, we look at the mass spectrum. Okay, and from there we identify the marker ion that can be used for identification, confirmatory, and quantification. So for the benefit of some of the audience who may be like getting to know about pyrolysis GCMS for the first time, I just want to briefly introduce about this technique. So pyrolysis GCMS is a kind of hyphenated technique. So where the pyrolyzer is attached to the injection port of a GCMS, and you are able to introduce a solid sample directly, and the outlet of the pyrolyzer is connected to the injection GC inlet, and that means all compounds are transferred to the GC column for separation and subsequently by detection by the detector. So one can see this micropyrolyzer is more like a sample introduction kit for solid sample analysis. How this is done is, yeah, if you look at this, so you have, let me put a, excuse me. Just give me a minute. So when you have a plastic particles, because this is actually for other polymer analysis, but the point is you can just transfer your particles into the sample cup. Then the sample cup is transferred to the furnace. So when you start the analysis, the cup drop into the furnace where the temperature is set high. So this sample goes for decomposition. Then the polymers will break down into the micromolecules. So that's the small molecules that will be swept with the help of carrier gas to the GC column, and where based on the retention coefficient and this partition coefficient, this will be separated, and you get to see compounds are like eluted one after other. with the detection suitable detector, you can see the peak for each type of compound. Okay. So this is a typical out chromatogram you get with the pyrolysis GCMS, be it a polymer or any environmental samples. So for a simple understanding, one can see the pyrolyzer is more like a sample introduction kit for direct analysis of solid samples in GCMS applications. Okay, previously I have shown a typical pyrogram of polystyrene. So in this slide, I'm showing the typical one for polyethylene and PMMA. So for each of these, okay, so they have a unique pyrogram, and also we can identify a marker ion that can be used for identification and quantification. Okay, for certain polymer like PET, even thermally assisted hydrolysis is recommended. So for getting a distinct peak, for example, if you look at the PET direct pyrolysis, so you have multiple peaks. Okay, so whereas if you do with methylation, so you have a very special unique peak, so that can be used for your identification. Okay, so this is a mass to charge ratio, the ion that you should consider if you are using methylation. Okay, so this is not something that we recommend for all analysis, but when you are specifically looking for PET at very low concentration, then we recommend to use this thermally assisted hydrolysis methylation. Excuse me, this. Hold on. So some microphone is on, so you may have to turn them off. Yes, give me a minute. Sorry. Okay. Yeah. Sorry about that. So this is what we say the marker ion for different type of polymer. So this can be used for identification and quantification. Okay. For example, for polystyrene, 91 and 104 is recommended. For polyethylene, 85, 83, 82, and so on and so forth. So you can see many of reports use this approach for microplastic analysis using pyrolysis GCMS. But there are challenges when you have these compounds like as a mixed microplastics. So this is what we have encountered during our development. We don't have a specific target, like we want to see any type of plastic particle present. And second thing is when you have multiple microplastics, so it may produce different pyrolysis. Okay, so these pyrolysis during the travel from the furnace to the column, it can lead to some secondary reaction, because of which you may miss out some of the polymer information, the microplastic information. And since it has multiple pyrolysates, separation also can become a challenge. So these are the things that we have looked to address and see how we can improve. And for data interpretation, because every polymer can produce multiple pyrolysates, so if you want to go manual data analysis, so that may really take a lot of your time. So we have come up with a software that can really like help you to do a one-click solution for data analysis of microplastics in environmental samples. Yeah, we also want to make sure that this is applicable for environmental samples. What have we done for this? Okay, so one is, yeah, the sample homogeneity is one of the important part. So if you don't have your sample homogeneous, then every time you repeat the analysis, you may have different data. So when you collect samples in filter sample, like filter paper, right? So the particles may not be evenly distributed. So if you analyze one portion of the filter, then if you do the multiplication, maybe you are overestimating or underestimating. So our recommendation in such situation to homogenize the entire paper with our cryo mill. So we have developed a cryo mill. It's about this IQ mill, the cryo mill that Frontier Lab has developed. It's just a small benchtop cryo mill that can be used for powdering a different solid sample, including our microplastic samples that are collected in filter. So as you can see, be it water sample or sediment or biota, finally they are collected on a filter paper. So this filter paper, some try to cut a portion and analyze directly, or some they try to roll the entire filter and put into the cup. So one limitation on our Py-GCMS, we cannot take a large mass of sample. Okay, so this is only 80 microliter cup. So because this equipment is mainly developed for polymer analysis. Now we are trying to use it for trace analysis. So there is some kind of mismatch, we can say. So, but we are trying to address these issues. So once you pulverize, so then this powder filter paper with microplastic can be transferred to this cup and analyzed. So it's not mandatory. You can also cut the filter or roll the filter if you are using small size filter paper. Okay. So the second development that we have done is a development of small God column that helps improving the separation of certain type of the polymers in the microplastics. Okay, so in terms of connections, it's very simple. So you just have to add this prior to the analytical column, and it also helps to protect your lifespan of your analytical column. So why we need this? Okay, so what we found when we did our standard analysis without the pre-column, we found the polyethylene pyrolysis C8 hydrocarbon and the nylon 66 cyclopentanone, okay, are being co-eluted. So with the pre-column, we were able to separate this. So it's really helping a lot. Otherwise, you may have to do separately the extracted ion chromatogram, which is not something everyone prefer. So the small addition of God column improves the separation of some of the polymers pyrolysis. So the third small hardware that we have developed is the glass insert. Okay, as you all know, GC, we have this glass insert. So what we have done, we have packed this glass insert with a packing material, which is basically a PDMS coated material. And this is helping a lot in improving the peak shape. We can see this, the polyethylene with the 100 microgram. What we can see here, some of the abnormal peak shape, with a lower peak height and broad peak. So the peak shapes are changing, which we can improve with the help of this packing material into the glass insert. So we highly recommend people to use this. Okay, and particularly for quantification, some of these hydrocarbons, we just want to show that it's really helping to have those peaks separated. The third thing is about the calibration standard, because you want to do the quantification, because mass bearing. So where was I? So yeah, so I was basically explaining about this calibration mixer. So we have this calcium carbonate matrix and silica, and I was telling about like why we chose this 11, 12 polymers, which is based on the literature. Also the common or most commonly used plastics in our consumption. So this is so. At the same time, we have additional database that will allow you to look at any polymer or plastic like outside this 12. Okay, so that's another extra database that we have as part of this software, which I will explain it later. Okay, so far I have told about a few things that Frontier Lab has done to simplify this microplastic analysis by pyrolysis GCMS. So one of the things that I told is for sample improving sample homogeneity. So we have this cryomal that can be considered, and for improving the separation, we have added a God column that can improve the separation of this polyethylene pyrrolizate and nylon 6 pyrrolizate. And the third one is the glass insert with the packing material that improves the peak shape of this polyethylene type polymers, so that your integration and also the quantification will be more precise. And the fourth one is the calibration mixer. Okay, so these are the main hardwares, okay, and that are required for this microplastic analysis. So in terms of the software, so we have developed this F-Search, because F-Search is our standard software for polymer applications. Okay, so we are in this polymer analysis field for 30 over years. So we have a database for 1,300 polymers. Okay, so where we can do this evolved gas analysis and pyrolysis, GCMS, also the additive analysis. So that means this F-Search is a kind of a trademark for our polymer search software. But the same thing we have customized for microplastic analysis. Okay. At the same time, I have to mention here, we thought initially we can use our same software, the one we developed for polymer. Unfortunately, that was not possible because of some selectivity issues. So we have to really develop a new algorithm that is suitable for this application. So that's why we have come up with this new name called F-Search MP. So our standard F-Search is meant for polymers, and this is F-Search for microplastics. So this F-Search microplastics, okay, so comes with a kind of whenever you buy this software, the calibration standard is provided, and sample preparation procedure is provided as well. And yeah, you have these two type of database for quantification, also the calibration standard, and it comes with the pre-column and also the other consumable parts. It's a kind of package, we call it, for microplastic analysis. Okay. So now let me briefly explain how this software is different from our standard software. So on top, what you see is the F-Search version 3.6. Now we are into 3.7. Okay. So for example, if you talk about polystyrene, so polystyrene produce three predominantly three peaks. Okay, styrene, styrene dimer, and styrene trimer. Excuse me. So in our standard F-Search software, we try to consider all three peaks mass spectrum. Okay, the mass spectrum of each of these peak, and we integrate it's like a summation of all this and use this mass spectrum for identification through our search algorithm. But in the case of F-Search, because we are doing such search in very small concentration where your peak abundance may be small compared to the standard polymer analysis. So to improve the selectivity, what we have done, so we have not used all peaks. We have only used selected peaks for this integrated, what is called, for the identification purpose. So for example, styrene dimer, and styrene trimer are the common peaks for polystyrene. But we use only styrene dimer and trimer for identification, but for quantification, only the styrene trimer. So the search algorithm is different from our standard one. So that's why it has to be a separate product by itself. So we basically looking at the retention indices. So later I will explain how this is done, and it will be compared with our reference the database. So this is automatic process, but how it works is basically in 4 steps. So when you have a sample analyzed, okay, so initially you have your database. This is a reference one, okay, the registered polymer in database library. And in B, what you say, you have an unknown sample. So in unknown sample, you want to search for polystyrene. Okay, so here I'm just showing polystyrene as an example, but when you use our software, it will look for all those 12 polymers automatically. You don't have to choose a polymer. So it will look for one after other polymer. Okay. So what we will do, it will look at the extracted ion chromatogram first, then look at the mass to charge ions. Then this will be combined. Okay. So finally, this combined spectra will be matched with our reference database. So it is a kind of four-step process. So first it will do the extraction of peaks, extracted ion chromatogram, then extraction of the mass spectrum, then combining the mass spectrum of these main peaks, then use this for peak match ratio, the matching percentage, then finally you will have the identification done. Okay, so this is how, but it is automatic. Okay, now let me quickly run through the workflow. Okay, so I have explained about all these hardwares. Now I can very quickly show how the analysis is done. Okay, so starting from sample preparation. Okay, when we say sample preparation, so sample collection is a different subject by itself. So what we say, you collect sample in appropriate manner for water samples or sediment or biota. After that, you have the samples either on a filter or you use cryomill to powder everything. And this powder you can weigh into this sample cup. Okay, then you can introduce them into the pyrolyzer. So, but we also have a auto sampler. So if your lab is doing more number of samples, we recommend to use the auto sampler. So that can really stack up to 48 samples in the carousel. So you can do a batch analysis of 20 or more or so on. So auto sampler is option. So some of the users will consider. So then this auto sampler will allow to run the analysis one after other. So in pyrolysis, the pyrolyzer, the sample cup will be dropped. In the pyrolyzer is set at high temperature. Then the GCMS will produce the data, okay, GCMS. Then this data is analyzed with the FP, the FSearch MP software. So this is very straightforward. So the first thing, before you start your unknown sample analysis, you have to do a calibration. Okay. For calibration, yeah, as we say, we recommend to do at least 3-point calibration. So that means you can use our calibration mixer, 4 milligram, 2 milligram, and 1 milligram. Okay. So even though you weigh 4 milligram, the actual concentration of polymers are much lower. Okay, in micrograms level, 160, 40, 80, and so on. So this concentration difference also based on the sensitivity. Okay, so for example, polystyrene is very sensitive and also nylon 6. So polyethylene, they are not really very sensitive. So we have to use a different concentration, okay, for this multiple or the mixer analysis. So you use 4 milligram, 2 milligram, and 1 milligram. And you analyze with the pyrolyzer, the Py-GCMS. So what you get is basically the data. Okay, this data you keep it one side. Okay. Then we move on to the data analysis part. Okay, so maybe I should have put one more slide. So when you do the analysis, you get something like this kind of pyrogram or chromatogram. Okay, so for each type of analysis, you produce this data file, right? So this data file has to be opened with our FSearch MP to really do the data analysis. So when you open, so first we recommend to use the highest concentration data file. Okay, open. Then we have to do the RI calculation from the reference sample. Okay, so this is our reference sample, and factory has got its own data, right? But in your lab, how this is same or different, something we do not know. So what we recommend, we have to use your own data to calibrate the retention index or the retention indices. Okay, so this is what we recommend, and at least you should have some kind of cross check For example, the toluene peak is expected to be around 5.88 minutes. But in your lab, if you are getting at 4 minutes or 7 minutes, you may have to pay an attention to your method, whether any of the parameter is not working. So it will automatically detect the RI for each of these four pyrolysates. Then you just have to click update. That means your software is updated for your own data. It is not working on the factory set data. So after that, the next step is create the calibration graph. So creating calibration graph, basically, yeah, you just have to have, we recommend to have at least three replicates. Okay. And for calibration level, you put it 3, and index level 1 is you just put the concentration for the first one. For second and third, it can just do the automatic calculation. That means the first one is 4 milligram, right? So for the second one, it is 2 milligrams. So that is 4 divided by, like 2 divided by 4 is 0.5. So if you put 0.5, then automatically the concentrations are calculated for the second point, and similarly for third point. So for each one, you put the concentration and you load the data file. Then you move to the index level to 2 and load the data file. So you have to do this for all 3 points, just uploading the data file. So after that, you click the process, you are ready to see the calibration graph. Okay, so this is the typical calibration graph. So we have produced this in our demo lab in Singapore. Okay, so this is for the polyethylene. So where we have done 3 replicates for 3 points. Okay, so we can see there are some variation, but yeah, this variation mostly can come from your sample weighing. Okay, so you have to be as precise as possible for weighing this mass. Okay, 4 milligram means it should not be 4.5 or 3.8. Every time you try to be within 10%, so that way you can have. So what you get to see here is the calibration graph for each. Okay, if you click on each one, you'll get to see the calibration graph and also the extracted ion chromatogram. And the table, what you see, the retention time and average area, then average height, all this. Okay, so this is all automatic. So I have just shown the calibration graph of this mixer, which was done in our lab. You can see we have obtained satisfactory linear calibration for all this mixer for these 12 polymers. So after that, when you have your unknown sample, you have to load your sample data into the software. Okay, then you have to load your quantification calibration data. So that was the one that we have previously done, right? So this data should be saved, and you have to load this quantification calibration data. Then you basically just press click. So once you click here, then what you see is this is the output. So that means you can look at what are the different type of polymer present in my sample. Okay, and what is the probability match. So this match, generally we recommend 90 and above, but when you have matrix sample, you can go down to 80%. But these are the things that something we cannot put as a rule of thumb. We have to make your own assessment and judgment. Okay, because how much you are able to treat the matrix in your sample can vary lab to lab. So our general recommendation is to keep the probability percentage 80 and above. But in some cases, if you are getting the results satisfactory, even at 70%, this is acceptable. Okay. So for each one, you can always compare the mass spectrum, also the extracted ion chromatogram. So based on that, you can always qualify the data before you can report it. So from this F-Search MP software, what you are getting is, okay, the information what you get is the library match quality data. As I said, this is one. Then the plastic name, okay, what are the different type of plastics you find in your sample, and also the quantity. So you can easily see how much is present in my sample. Then relative amount, this is something we may not be, because this is only for composition analysis, but that also we can see it. Okay. So all this information is given. Even the LOQ also is shown for each type of method. So this is a typical extracted ion chromatogram and the mass spectrum for each type of polymer, which we can always compare with the reference database. Okay, so this method, what I have explained so far, is suitable for microgram level analysis. Okay, our lower limit of quantification mostly fall in the range of 13, okay, and as low as 0.34. So we can say. So the quantification limit is calculated based on the 10 sigma of our multiple analysis. So if you are really interested to do 1 microgram to 100 micrograms, like type of mass-based analysis of microplastics, so this is already a good technique, a good method to be followed. Okay, but now people are interested even in below 1 microgram. Okay, so that means in some of the samples you may have only very few particles. And these particles may have very small mass of microplastics. So that means this may not be sufficient. You may have to go for a different approach. Excuse me. Okay, so but before going to the second part of this nanogram level analysis, let me just show one of the real world sample analysis. So this was a sample from our collaborator in Germany. Like they have collected sample from North Atlantic Bay in Spain. Okay, so they have, this is actually a sediment sample. So they have done the density separation followed by the organic treatment. Okay, then this is the sample. So as I said, for homogeneity purpose, they have, because when you have a lot of particles, then you can always homogenize before the analysis. Okay, so this is the output of this unknown sample. There are two sediment, one from the offshore, other one from the coastal sediment. So this data has been analyzed with our software, and you can see the difference. Okay, both samples have got multiple polymers. Okay, but PVC is predominantly present in this coastal sediment sample. Okay, whereas polyethylene is more in this offshore sediment sample. Okay, so this is one kind of example how this Py-GCMS is used for the environmental samples, be it water or sediment. Okay, so let me move on to the second part. So I'm just running a bit late because of the technical issues, but I'll try to wrap up quickly. Okay, some of our researchers, or even we are interested in a nanogram level analysis of microplastics. As you all know, because we are using GCMS for a trace analysis for microorganic pollutants. Usually what we do, we reduce our split ratio so that you are able to transfer more sample into the column and detector. So in some cases, we also consider splitless injection. So the question, are we able to use splitless injection for polymer analysis or the microplastic analysis? So the answer is kind of no for this. The reason, when you use splitless injection, your carrier gas flow is reduced. Okay, in split mode, generally it will be 50 milliliter per minute or 100 milliliter per minute, depending upon your split ratio. But in splitless, it will be 1 ml to 2 ml per minute. So in such flow rate, okay, such lower flow rate, the compounds stay in the furnace for some time before it will be reaching the column. So during this phase, right, so there is a possibility for secondary reaction. So this example shows that. Okay, so we have done a 25 microgram of polystyrene, so where we have styrene peak and trimer peak. Okay, then we have done splitless with the 0.25 mg. So we have reduced the concentration, but what we have seen, the styrene trimer peak is almost like reduced. This is because of this secondary reaction that converted every trimer into styrene. So because of which we see the substantial difference in the split ratio, the ratio of this styrene trimer versus the styrene. So the answer is we cannot use standard splitless injection for nanogram level microplastic analysis. So then how to address this or how to go about it? So that's the question that we have. So what we wanted to address, okay? So our objective, basically we want to have a technique that will allow you to do the nanogram microplastic analysis. But same time, we want to use our standard injection port with splitless injection, okay? And this should be compatible with all type of GC and easy to operate. So for this, as I mentioned, the main problem is the flow rate, right? So we have to optimize the carrier gas flow rate at which secondary reactions are suppressed, okay? This is one thing. Then at least we should be able to get the concentration like 50 to 100% of the theoretical value. Then it should also produce a linear calibration curve and reproducibility equivalent to splitless GC. Okay, so you can understand the problem because we want to do splitless analysis. At the same time, we have to keep the flow rate high. Okay, so this is a kind of tricky situation. So how we can address this is what our R&D people effort is here. Okay. So our lab has come up with a kind of new device. Okay, it's called multifunctional splitless sampler. Okay, so what it has got like three things. Okay, so one is the pre-column, the second one is the splitter, and third one is a kind of some solenoid valve for pumping the system for increasing the flow rate during the analysis. Okay, so let me briefly show what it means. Okay, so when you have your sample injected in splitless mode, okay, you have your flow rate low, so because of which it may stay here for some time, so that leads to secondary reaction. So we want to avoid that, so we have come up with this external hardware that can help you to. So how this is helping? Okay, so we have this pre-column. This is not a deactivated column. This is with some coating. So that means it is more like a pre-concentrator, we can tell. Okay, so what happens? You keep your split, the injector in split mode. Okay, at the same time, we use this suction pump and set the flow rate 10 to 20 milliliter per minute. And this will be sucking the samples from the furnace, okay? And it will be exhausting because this is a column of with some retention. So all those polymers will retain here, only the excess gas will be going out. So what we are doing basically, we are trying to keep the flow rate high enough here, okay, so that secondary reaction is not happening. At the same time, we use the pre-concentrator so that we are not losing the sample. So that is step one. Step two, then we switch to the splitter and we send this sample with the normal split analysis mode. Then we will close this one. So this pump is used only during the first stage of collecting or pre-concentrating the pyrolysis into this column, pre-column. Then we will switch off this, then it will run on the standard split analysis mode. So we are able to get similar sensitivity. So this is what we can see from this. So this is the normal output with this new setup. But one problem we have seen, when you do the second analysis, there is a broad peak. So this could be because of the dead volume in this pre-column. Okay, so that we try to address in our second approach. So what we have done here, so previously I have shown pre-column, splitter, and suction pump. Now we have added one more, okay, flow controller for the helium. So this will help to backflash the column, okay, after the analysis, so that you don't have any dead volume and it does not interfere in your subsequent analysis. Okay, so this is the steps. Okay, first you pre-concentrate in the pre-column, then you start the GCMS analysis, and you do the backflash of the pre-column so that your next analysis is not affected. All this controlled through this small controller. Okay, this is called multifunctional splitless sampler. So by doing so, you can see here. Okay, so the first thing what we have verified for this module, okay, we have done the split GC analysis first with the 1 to 50, and where, yeah, we have got the signal for all these peaks, and we have done the splitless. So that means in splitless we need to have improved sensitivity, so that's why the factor is 52, 50, 51. And we have done same with our new splitless setup, and we do the pre-cut of this solvent also, and we can see that these results are quite comparable. Okay, so this was one of our objective. Even though you are using this multifunctional splitless sampler, the data should be something equivalent to the conventional splitless. So bear in mind, we have not taken polymer, we have taken a normal hydrocarbon, because once it becomes polymer, we cannot do this comparison, okay, because of the secondary reaction. So we have taken the long chain hydrocarbon for this comparison. Okay, and this tells the new device is working, okay, for splitless analysis. So that allows you to do the low level analysis. Okay, so we have further verified the linearity, because as I said, that was our purpose objective also. We have verified the linearity, we have reduced the reproducibility. So after we have done this first evaluation with the organic, like a long chain hydrocarbon, then we have to test or evaluate with the polymer. Okay, so with the polymer, okay, the first one is the standard split mode analysis, and you have this ratio of trimer to styrene is 22.3, and conventional, yeah, as expected, this is low, and this is the new splitless sampler with the GC. So where you can see again the ratio is improved. So that means this system, this multifunctional splitless sampler is working for splitless analysis of Py-GCMS. Okay. So as I mentioned earlier, this is basically is in three-step process, but it is automatic. Okay, first you have this trapped in pre-column, which is done with the help of suction pump. So where the average flow rate will be 20 to 30 milliliter. So the polymers pyrolysis will be trapped here. Then you do the analysis. After analysis, you do the backflash with this. So by doing that, you are able to use this equipment for continuous analysis. So the other parameters that may affect or influence the analysis is because we are going with the flow rate and also the temperature variation, how it is actually affecting the linear velocity of the carrier gas is what we have to investigate. So what we have seen, okay, normal GCMS constant flow is okay, but when we use this multifunctional splitless sampler with GCMS, we found the constant pressure mode will be much better for improving the sensitivity than constant flow mode, because in constant flow mode we felt the sample is losing when this pump 3 is. So later I will explain what exactly it means. Yeah, so the point that I want to highlight from this, constant pressure mode is a recommended condition for operating this multifunctional splitless sampler. Okay, so particularly what we see that the P3, right? So the suction pump, if it is operated in constant flow mode, the flow rate is constant, like automatically increase with respect to the temperature, because of which it is losing some of the annulates. So, but by keeping the constant pressure mode, you are able to control this, and your sensitivity is substantially improved. So another important finding during this development, our pre-column is expected to retain all these pyrolysates. At the same time, to improve the sensitivity, we found cryotrap can be attached. Okay, why we say that? Okay, so we have taken this sample. Okay, the N-alkenes from C9 to C34. So what we can see, we cannot find with the new splitless sampler anything below like C9. It's mainly because we are losing them. But with the cryotrap, this can be improved. So for overall improvement in sensitivity, okay, now we can see with this. Without cryotrap, you are not able to see the compounds of C6 to C10. With the cryotrap, you are able to see. So this is another addition. So if you are using our multifunctional splitless sampler, so cryotrap has to be included as well for improving your sensitivity. Okay, so to confirm this for the analysis of a polymer, okay, so we have taken this one of our environmental samples. So what we are trying to show in this slide, the improvement in sensitivity, okay, with the cryotrap, and this is secondly, you are doing the split analysis with the 1 to 50. So where your signal to noise ratio is 27 and 75. With the splitless, it is almost like 50 times more. Okay. So this is what basically the splitless analysis will do it for you. So that means you are able to do the very low level analysis of microplastics. So to demonstrate this with the nanogram level microplastics, because as I said, preparation of standard is always a challenge. So what we have done, we have taken this polyethylene 1 milligram, okay, the size of 10 microns, that has been diluted 1000 times using this silica. Then we have done the cryomilling to powder everything. Then we have weighed this into 0.01 milligram to 50 milligram. Okay, so here the polyethylene is already diluted to get this nanogram level. Then we have taken this sample. So we are able to see the signal, okay, even for 0.1 microgram of polyethylene versus in split ratio, this is 5 microgram. Okay, so when we say 5, its actual concentration may be like 0.1. Okay, in this case, we have not used the liquid nitrogen, and the second one we have used liquid nitrogen. So what it means, when you use very small mass, then liquid nitrogen, the cryotrap is really helping a lot to retain your samples. Okay.
Next, we compared the
Excuse me.
Next, we compared the reproducibility of each analytical method and
Yeah.
signal to noise in scan mode and SIM mode.
This is actually this.
Reproducibility was inferior for the new splitless method. However, there are less.
Okay, sorry about that. Yeah. So in this, what we have done is we have compared some problem again. Yeah, so we have compared the results for the split and the splitless analysis. Okay, the splitless, the splitless analysis we have done in scan mode and sim mode. The sim mode can improve the sensitivity, the reproducibility, particularly for this low-level analysis. Okay, so that means we recommend to use a sim mode analysis when you are doing nanogram level analysis with this multifunctional sampler. Yeah. So we have verified the linearity of these multiple compounds. Excuse me. So let me some problem there. Yeah. So you can see the linearity is very good for like 0.1 to like up to 100 milligram. It is comparable to the split scan mode also.
The lower limit of quantification.
Okay, so this slide basically shows the lower limit of quantification, okay, based on the signal to noise ratio. So with the split ratio, okay, so your lowest detection can be like 1 microgram, okay, whereas in new splitless it can go to 0.05, and with the sim mode it can go to 0.01. Okay, so this is for C21 mononin. If it is for C21 diene, so the split ratio will be 5, and with the scan mode it will be 0.1. Okay, then for sim mode it can be 0.01 microgram, so which is basically 10 nanogram. So what we can see here, so new splitless method and sim actually offer you 100 times higher sensitivity.
Next, we will show an example.
Okay, so I will try to wrap up this with the one application, okay, to investigate this applicability for nanogram level analysis. So we have taken a real unknown sample, okay, collected from this Comilo Beach in Hawaii, the US. So actually this sample we got it from EPA that has been diluted with silica. Then yeah, after homogenizing with the cryomil, we have taken a sample of 0.1 milligram. So this 0.1 milligram, okay, actually shown the concentration as 23.3 nanogram. So, but this is actually after the dilution. So the actual concentration in the sample is around 0.233 milligram. Yeah. So just to demonstrate the applicability of this multifunctional splitless sampler for nanogram level analysis of microplastics. So I have shared the different hardware that are developed for making this splitless pyrolysis GCMS analysis possible for nanogram level microplastic analysis. So here, since we do not have a real sample of such nanogram level, so we have taken this microgram level sample and diluted, okay, just to demonstrate the applicability. So with that, I would like to wrap up this presentation. So pyrolysis GCMS is a simple and fast technique for microplastic analysis in drinking water and other environmental samples. So Frontier Lab has developed accessories like UAMP column kit, calibration standard, glass insert, MP software, which enable rapid analysis of MP for both identification and quantification. For nanogram level analysis, we have developed new splitless sampler, which overcome some of the challenges that are there for polymer. Okay, so pre-column splitter, suction pump, backflash, cryotrap are key components to achieve good sensitivity through this splitless Py-GCMS analysis. With that, I would like to thank you all for your kind attention. So if there are any questions, I will be happy to answer them.